आज आपण भौतिकशास्त्रातील केमिकल इफेक्ट ऑफ करंट या टॉपिकवरती चर्चा करणार आहोत. या देखील टॉपिकचा संबंध आपण नेहमी बघतो, व्यवहारात गोष्टी ज्या बघतो त्यांच्याशी आहेच. माझं नाव डॉक्टर वर्षा जोशी. मी पुण्यातील नवरोजी वाडिया कॉलेज इथे 30 वर्ष भौतिकशास्त्र शिकवण्याचं काम केलं. 2003 साली मी रिटायर झाले. त्यानंतर आता विज्ञान विषयक लिखाण करण्याचं काम हाती घेतलेलं आहे. माझं वाद्यांमधील विज्ञान हे पुस्तक प्रकाशित झालेलं आहे. स्वयंपाकघरातील विज्ञान हे देखील पुस्तक प्रकाशित झालेलं आहे. विज्ञान सौंदर्य प्रसाधनातील हे पुस्तक प्रकाशनाच्या वाटेवर आहे. आणि साप्ताहिक सकाळसाठी मी वस्त्रांमधील विज्ञान हे सदर किंवा ही लेखमाला सध्या लिहित आहे. विज्ञान विषयक लेखन करणं आणि विज्ञानाविषयी बोलणं ही एक केवळ आनंदाची गोष्ट आहे. तेव्हा आता आपण केमिकल इफेक्ट ऑफ करंट या विषयाला सुरुवात करूया. हा जो इफेक्ट आहे तो मायकेल फॅरेडे या प्रख्यात भौतिक शास्त्रज्ञानं 1833 मध्ये शोधून काढला. सो केमिकल इफेक्ट ऑफ इलेक्ट्रिक करंट was studied by Faraday in 1833. He found that when an electric current passed through a conductor, no chemical effect is produced in the conductor. However, when electric current is passed through some liquids, they do display the chemical effect. In this respect, liquids are divided into 3 classes. म्हणजे नॉर्मल सॉलिड जे कंडक्टर्स असतात त्याच्यातून जर आपण इलेक्ट्रिसिटी पास केली तर त्यांच्या केमिकल कॉम्पोजिशन मध्ये कुठला फरक पडत नाही. पण आपण लिक्विड मधनं तीच इलेक्ट्रिसिटी पास केली तर मात्र हा फरक होतो. आता हे लिक्विड्स कोणत्या प्रकारे रिस्पॉन्ड करतात ते बघूया. सम लिक्विड्स डू नॉट अलाव इलेक्ट्रिक करंट टू पास थ्रू देम. फॉर एक्झाम्पल डिस्टिल्ड वॉटर, व्हेजिटेबल ऑइल एटसेट्रा. सम लिक्विड्स अलाव करंट टू पास थ्रू देम but do not dissociate into ions. For example, mercury. Some liquids allow current to pass through them by dissociation into ions. For example, salt solutions, acids, bases, etc. Let us now see what are electrolytes. The substances which dissociate into ions and when in solution form allow electric current to pass through them are called electrolytes. What are the examples of electrolytes? Acids, bases, acidulated water, salt solutions such as copper sulfate solution, silver nitrate solution, etc. Amongst electrolytes also there are 2 types. One is strong electrolytes, the other is weak electrolytes. Which are strong electrolytes? Those electrolytes which are more or less completely ionized in their solutions are called strong electrolytes. For example, HCl, NaOH, NaCl. Weak electrolytes are those electrolytes which are ionized to a small extent in their solutions, and these are called as weak electrolytes. What are the examples? NH4Cl, CH3COOH, H2CO3. Using these electrolytes, we can carry out a process of passing electricity through them, and that is called as electrolysis. So the process of liberating free elements from an electrolyte solution when electric current is passed through it is called electrolysis. Suppose copper sulfate solution is taken in a vessel and current is passed through it by using 2 electrodes and a source of EMF. Now the electrode through which the current enters the electrolyte is called anode and the other electrode is called as the cathode. On passing current, then copper ions, which are positive ions, drift to cathode, while sulfate ions, which are negative ions, drift to anode. At the cathode, these positive copper ions discharge themselves and copper atoms are liberated at the cathode. The vessel in which electrolysis is carried out is known as a voltameter or an electrolytic cell. Here, remember the difference. A voltmeter is a device that measures the voltage or a potential difference, whereas a voltameter is an electrolytic cell used for electrolysis. Now we are going to talk about the theory of electrolytes. How come the electrolytes do not dissociate into ions in solid form, but they do so in solution form? An atom or a group of atoms or radical having charge is called an ion. If an atom, a molecule or radical has electrons less than what it would have in the normal state, it is called positive ion. The positive ions are known as cations and they are attracted towards cathode. During electrolysis, these are collected at the cathode. On the other hand, if an atom, a molecule or radical has electrons more than what it would have in the normal state, it is called a negative ion. These negative ions are known as anions and they are getting collected at the anode. During electrolysis, these are collected at the anode at room temperature, and electrolyte has a conductivity about 10 raised to minus 5 to 10 raised to minus 6 times that of good metallic conductor. Now why is the conductivity so low? That is because of the following reasons. The number of free ions per unit volume in an electrolyte is quite smaller as compared to the number of electrons per unit volume in a metallic conductor. Second reason, compared to electrons, ions have large mass. Therefore, when an electric field is applied, they drift much more slowly than electrons. An electrolyte solution is quite dense. As a result, the ions experience more difficulty to drift through it. It is because of these three reasons that the conductivity of the electrolytes is lower than that of the metals. Now the force of attraction between ions in an electrolyte is very strong. Therefore, there is a higher potential energy. When in solution, the potential energy decreases so much that thermal energy is sufficient to dissociate the electrolyte into ions. And that is why the electrolytes get dissociated into ions when they are in solution form. Now what we are seeing is the picture of a copper voltameter. This copper voltameter is a glass vessel in which there are two electrodes, anode and cathode, and there is a power supply, that is battery, which is connected to ammeter. The ammeter is connected to anode, and battery negative terminal connected to a rheostat or variable resistance, then a key and to cathode. Let us once again read this description over here. The circuit consists of a vessel containing copper sulfate solution in which two copper electrodes are immersed. Anode is connected to the positive terminal of the battery through an ammeter. Cathode is connected to the negative terminal of the battery through a key, and rheostat, which is the variable resistance. The solution is made slightly acidic to improve electrolysis. Now over here is a link. Anyone interested in seeing the actual instrumental setup and working can go to this link and see the particular setup. When current passes through the solution, it dissociates and ions are produced as follows. Copper sulfate dissociates into copper positive ions and sulfate negative ions. Water decomposes or dissociates into positive hydrogen ions and negative OH ions. The positive copper ions drift towards the cathode C. As they reach C, the negative terminal of the battery releases two electrons to the cathode. These electrons combine with the positive copper ions to give copper atoms which are deposited on the cathode C. The reaction is as follows. The positive copper ions plus two electrons will give us the copper atom. The anode releases two electrons which flow towards the positive terminal of the battery, creating a positive copper ion which combines with the sulfate ion to produce copper sulfate. Therefore, copper, it gives us copper ion, positive copper ion and two electrons. That is the reaction. Therefore, circuit gets completed and the current keeps on flowing through the electrolyte, depositing copper on the cathode. The sulfate ions combine with copper ions to give copper sulfate, as a result of which the concentration of copper sulfate solution remains the same during the process of electrolysis. For electroplating of metals like silver, gold, copper, the process of electrolysis is used. There is another voltameter called as water voltameter, which is used for obtaining hydrogen and oxygen. We can see the experimental setup here, the glass vessel containing water. Once again, the circuitry over here which supplies the current with the ammeter, battery, key and the variable resistance. Let us once again read about this. This consists of a glass vessel containing acidic water. A provision for 2 platinum electrodes is made, over which 2 long tubes filled with acidic water are held in inverted position. The anode A is connected to the positive terminal of the battery through the ammeter, and cathode C is connected to the negative terminal of the battery through a key and a rheostat. The current value is adjusted and it is made to flow through the water. The electrons from the negative terminal of the battery enter the cathode through connecting wire and cause the following reaction. 4H2O plus 4 electrons give us 4 OH ions plus 2H2. That means hydrogen is liberated. So due to this, the hydrogen gas is liberated at the cathode. Also, the concentration of OH negative ions increases. At the anode, the 4 electrons are released in the reaction 2H2O, giving us 4 positive hydrogen ions plus 4 electrons plus O2. Combining these 3 reactions, we can see that we get 2H2O giving us 2H2 plus O2. Hydrogen gas is liberated at the cathode, whereas oxygen is liberated at the anode. And the positive hydrogen ions combine with the negative OH ions, giving us again H2O. Based on this process of electrolysis, Faraday composed 2 laws. The first law states as follows. It states that the mass of the substance deposited at the cathode during electrolysis is directly proportional to the quantity of electricity or total charge passed through the electrolyte. Let M be the mass of the substance liberated when charge Q is passed through the electrolyte. Then according to Faraday's law, M is proportional to Q. Therefore, M equal to ZQ, where Z is a constant of proportionality. This is called as electrochemical equivalent, ECE abbreviated, of the substance. If a constant current I is passed through the electrolyte for time t, the total charge flowing through the electrolyte will be Q equal to I into T. Therefore, equation for M will be M equal to Z into I into T. Now the original equation for M was M equal to ZQ. If Q happens to be 1 coulomb, then M will be equal to Z into 1 equal to Z. If Q happens to be 1 coulomb, then M is equal to Z into 1, that is equal to Z. On the basis of this, we can define the electrochemical equivalent in a different way. The electrochemical equivalent is then defined as the mass of the substance deposited at the cathode when 1 coulomb of charge passes through the electrolyte. SI unit of electrochemical equivalent is kilograms per coulomb. However, this is a large unit, therefore it is usually expressed in terms of grams per coulomb. Following is the table which gives electrochemical equivalent values for different elements. We can see that the electrochemical equivalent for silver is the largest. What is the interpretation? What is the interpretation that we can draw from this? The interpretation is that if equal charge is through all these, then maximum deposition will be that of silver. Let us look at Faraday's second law. This states that if the same quantity of electricity is passed through different electrolytes, masses of the substances deposited at the respective cathodes are directly proportional to their chemical equivalents. Now, what is this chemical equivalent? It is atomic weight divided by valency. Let M be the mass of the ions of a substance liberated whose chemical equivalent is E. Then according to Faraday's second law of electrolysis, M is proportional to E. Therefore, M equal to a constant into E. Therefore, M upon E is a constant. Let us now find out the relation between chemical and electrochemical equivalent. Consider two different electrolytes with E1 and E2 as their chemical equivalents. On passing the same amount of electricity through these electrolytes, let M1 and M2 be the masses of the substances liberated respectively. According to Faraday's second law, M1 upon E1 equal to M2 upon E2. Therefore, M1 upon M2 is equal to E1 upon E2. If Z1 and Z2 are the electrochemical equivalents of the two electrolytes respectively, and the charge passed is Q, then from Faraday's first law, M1 equal to Z1Q and M2 is equal to Z2Q. Therefore, M1 upon M2 is equal to Z1 upon Z2. Now from earlier equation 3, we get Z1 upon Z2 is equal to E1 upon E2. Therefore, we can write E1 upon Z1 equal to E2 upon Z2. That means E upon Z is a constant. This ratio of chemical equivalent to the electrochemical equivalent is called as Faraday's constant F and is equal to 96500 coulombs per mole. Faraday's constant can be expressed in terms of the Avogadro number and electronic charge also, and that will be as follows. Suppose the valency of the atoms of the deposited substance is P. This means P electrons have to pass through the electrolyte to deposit one atom of that substance. This means charge Pe has to pass through the electrolyte for one atom of the substance to get deposited. If N is the Avogadro number, then the charge required to deposit 1 mole of a substance is N into Pe, that is NPe. If M is the mass of 1 mole of the substance, it follows that when Q is equal to NPe, the deposited mass must be equal to capital M, that is the molar mass. From Faraday's first law, we know that capital M equal to ZNPe or M upon P is equal to ZNE. But M upon P is what? It is chemical equivalent of the substance, which is E. Therefore, E equal to ZNE. But F is E by Z. Therefore, we have ZNE upon Z, that is F equal to NE, which tells us that the Faraday constant is Avogadro number multiplied by the electronic charge. Faraday constant is equal to the product of the Avogadro number and electronic charge. Since the Avogadro number N is 6.0229 into 10 raised to 23 and E is 1.602 into 10 raised to minus 19 coulombs, we have F equal to NE equal to 6.0229 into 10 raised to 23 multiplied by 1.602 into 10 raised to minus 19, which is 96,487 coulombs per mole, which is very close to 96,500 coulombs per mole. Let us now see what are the uses of electrolysis. The chemical effect of current, that is electrolysis, is used commercially for many things. The first is electroplating. Process of depositing thin layer of metal on any surface by electrolysis is called electroplating. The article to be deposited is made the cathode and the metal to be deposited is the anode. A soluble salt of the metal to be deposited is used as electrolyte. When the current is passed through the electrolyte, a thin layer of the metal is deposited on the article. Common examples are copper plating of steel utensils, silver plating of brass utensils, gold plating of silver jewelry, and chromium plating of furniture, etc. Second application, extraction of metals from ores. An example of this is the extraction of aluminium from bauxite, that is Al2O3, and cryolite, that is Na3Al(F6). Electrolysis also can be used for purification of metals, which is the third use. Here, impure metal is made as anode, pure metal is made as cathode. Soluble salt of pure metal is used as electrolyte. On passing current, pure metal gets deposited on the cathode. Copper can be purified by this method up to 99.99%. The fourth use, electrotyping. Exact copies of the metallic type used in printing works and of the engraved blocks on metals can be prepared using electrolysis. Exact copies of the metallic type used in printing works and of the engraved blocks on metals can be prepared using electrolysis. The impression of the type of block is first obtained on wax. The mold is made conducting by coating it with graphite powder. Then a thin film of copper is deposited by the process of electrolysis. The sheet gives a copy of the type of the block. Fifth application, preparation of caustic soda. By the process of electrolysis of sodium chloride solution, caustic soda, that is NaOH, is manufactured. Then there are several other applications. Electrolysis is also used for making capacitors with large capacitance. It can be used for local anesthesia by rendering a nerve insensitive to pain. It can be used for nerve stimulation for polio. It can be used to remove unwanted hair on the body. And it can also be used for chemical analysis and for rectifying alternating EMF up to 40 volts. After seeing all these applications, now let us go through some questions and problems. First question, how is the electrical conductivity of an electrolyte affected by increase in temperature? Due to increase in temperature, the electrical conductivity of an electrolyte increases. Can AC be used for electrolysis? Well, the answer is no, because if AC is used, electrolysis will take place alternately in opposite directions and hence no deposit of ions will take place on any electrode. Third question, what are the conductors of second kind? The electrolytes in which current is conducted through the ions are called the conductors of the second kind. In metals, the current is conducted by free electrons, so metals are conductors of the first kind. Another question, how the process of electrolysis can be used to find error in the ammeter? The current passed through an electrolyte can be calculated knowing the amount of time for which the current is passed, mass of the substance which gets deposited, and the electrochemical equivalent. The difference between this calculated value and the value shown by the ammeter in the circuit gives the error. Now let us go through some problems. First problem. A brass rectangular plate 10 cm by 3 cm is to be electroplated with copper. If it is to be coated with a layer 0.02 millimeters thick on both sides, how much time will it take with a constant current of 5 amperes? Certain quantities are given, namely electrochemical equivalent for copper equal to 33 into 10 raised to minus 5 grams per coulomb, density of copper equal to 8.9 grams per cc. Let us go through the solution now. Total area of the plate to be coated, 10 into 3 into 2, that is 60 centimeters square. The factor of 2 is included here because we are going to plate or rather electroplate the brass plate on both sides. Thickness of the copper layer to be coated is 0.02 millimeters, that is 0.002 centimeters. Therefore, volume of copper to be deposited will be 60 into 0.002, that is 0.12 cubic centimeters. Mass of copper, therefore, which is to be deposited will be equal to density into volume. So that will be 8.9 into 0.12, which gives us 1.068 grams. So much of copper is to be deposited. Now let T be the time taken to make this deposit. Then M equal to Z into Q, so Z into I into T. Therefore T will be M upon Zi. M is 1.068 and the electrochemical equivalent Z is 33 into 10 raised to minus 5. Current is 5 amperes. When these values are substituted and the mathematics is worked out, T happens to be 647 seconds. That means the time taken to deposit the copper will be 10 minutes and 47 seconds. Second problem. A steady current of 5 amperes is maintained in a copper voltameter. Calculate the time required to deposit 2.5 grams of copper. Relative atomic mass of copper equal to 63.5. Faraday constant 96,500 coulombs per mole. Solution to this problem. First, before going through the solution, let us go through the given quantities. M is 2.5 grams, I is 5 amperes, F is 96,500 coulombs per mole. Chemical equivalent for copper will be E equal to atomic weight upon valency 63.5 upon 2 equal to 31.75 grams per mole. M is given to us as ZIT, but Z equal to E by F. Therefore, M equal to EIT upon F. Therefore, T is equal to MF upon EI. Now we substitute all the quantities and get this as 1519.6 seconds, that is 1520 seconds. Therefore, time required to deposit the copper will be 25 minutes and 20 seconds. Now let's go to problem 3. This problem deals with the water voltameter. A steady current of 5 amperes is maintained in a water voltameter for 300 seconds. Estimate the volume of hydrogen evolved at standard temperature and pressure. Faraday constant equal to 96,500 coulombs per mole. Relative molecular mass of hydrogen 2.016, molar volume at standard temperature pressure is 22.4 liters. Current is given to us as 5 amperes. Time is given to us as 300 seconds. Therefore, total charge that is passed will be Q equal to IT equal to 5 into 300, that is 1500 coulombs. Molar mass of hydrogen is given as 2.016. Atomic mass of hydrogen will be therefore 2.016 upon 2, that is 1.008, and valence is 1. Therefore, chemical equivalent E equal to 1.008 upon 1, that is 1.008 grams per mole. Now, charge required to liberate 1 molar mass of hydrogen will be 96,500 divided by 1.008 into 2.016, and therefore that will be 96,500 into 2 coulomb. 1 molar mass of hydrogen at STP requires volume 22.4 liters. So for 22.4 liters, if so much of charge is there, then for volume of hydrogen evolved at STP on passing 1500 coulombs, what will be the volume? This is what we are going to calculate. 1 molar mass of hydrogen at STP requires volume 22.4 liters. Therefore, for 22.4 liters, the charge required is 96,500 into 2 coulombs. Therefore, for charge equal to 1500 coulombs, we are going to see how much will be the volume of hydrogen evolved at STP. And that is given by 22.4 upon 96,500 into 2 into 1500, which is 0.1741 liters. Therefore, the volume occupied by hydrogen is 0.1741 liters. We have gone through the entire process of electrolysis, the uses of electrolysis, and some questions and problems. It had been a very interesting session to discuss all this with you, and thank you.